artificial intelligence. It is my privilege to introduce you all Dr. Asvija B. Dr. Asvija B is serving as a scientist and a mission director at CDAC Bangalore. His primary research interests lie in the development of indigenous quantum software stack, hybrid HPC quantum computing, and quantum algorithm and applications. He has led several nationally significant projects supported by the Ministry of Electronics and Information Technology and Department of Science and Technology, Government of India. In his role as a mission director at CDAC, he is spearheading the organization's efforts in advancing the hybrid HPC quantum computing mission. He has been instrumental in the development of simulators for quantum network modeling, quantum communication, and quantum classical co-workflow simulation. His other area of research include visualization security, parallel computing, debugging, and profiling. He has played an active role in the design and setting of the Garuda Grid, the National Grid Computing Initiative of India. He has been actively involved in the grid projects with the attempts to link the European and US grids with the Indian Garuda Grid. He has many research papers in international conferences, journals, and a patent to his credit. It's really an inspirational profile, sir. Now, without wasting too much of our time, I request you to please start the session. Over to you, sir.
Thank you, ma'am. Thank you, Ashwini ma'am, for that wonderful introduction. So at the outset, I would like to express my gratitude for Vidyavardhini College for arranging this entire FDP and having me invited as one of the resource persons for delivering the talk over here. Thank you, the entire management of the Vidyavardhini College and also the specific people who are involved in the organization and conduction of this entire event. So in the interest of saving the bandwidth, I will just switch off my camera at this point. Probably when I conclude my presentation, I'll just switch on the camera for taking up any questions later on. Let me just try to share my screen. Please confirm if my screen is visible.
Yes, sir. Yes, sir. It is visible.
Thank you. Thank you. Yeah, sure. Okay. So let me begin my presentation with this famous picture, which again tries to bring back some dreadful memories to most of us. I'm sure most of you have already recognized this picture of the coronavirus and all the kind of trauma this virus had introduced some of the years back, right? What you see over here is the blown up picture of the virus itself, and the kind of projectile items that you see. There is this spherical element in the center, and then we also have this projectile elements that are coming out of this sphere as such, right? So these are basically what are called as the spike proteins of the virus. Now, the way the coronavirus infects or attacks the human body is that the human body has proteins which are called as receptors as such. Now, there are multiple such receptors, and if you can see the picture on the left side of the slide, we have something called as ACE2, which has been marked. So ACE2 happens to be one of the receptor protein as such, which is present abundantly in the human body. And specifically, these receptors are very much available. They are physically present in the respiratory tract, including the nasal area as well as the throat region. Now, the way the coronavirus attacks is that these spike proteins that you see, the projectile things that you see, they get bound with these receptors, the receptor proteins that are available in the human body. So this is one of the reasons why we all remember that we were asked strictly to wear the masks during this period of infestation, just to avoid these spike proteins from the virus itself to get bound with the receptors that are present in the human body. So this is one way in which you could reduce, or in which you could avoid the infection as such. Now, we all know that there was tremendous effort that was put up for coming up with an effective medicine, an effective drug that could inhibit the proliferation of this virus, or that could inhibit the way this virus attacks the human body. So basically, now that we have understood the way in which it attacks the body, so the simple way is that if you can neutralize this protein binding, the spike protein getting bound to the receptor proteins that are abundant in the human body, if you can somehow neutralize this mechanism, then you are efficiently neutralizing the functionality of the virus itself, and you would have found out a medicine against this particular disease as such. Interestingly, now there was huge concerted efforts worldwide to come up with an effective medication, or to come up with a drug which could effectively bring out this kind of effect that we were witnessing. In the United States, there was a huge consortium which was formed as the COVID-19 High Performance Computing Consortium. Basically, it is a group of multiple research institutes who all owned very high capacity supercomputing facilities, which are again called as high performance computing facilities. So there was a consolidated effort to put all of these facilities into a single unified grid kind of fashion. And if this entire huge facility could be put into use for coming up with
யாரா இவன் கிளாஸ் சீடாக்குல இருந்து எடுக்கிறான் டேய் டேய் யாரா சாமி
hello. Okay. Yeah, so I was talking about the effort called as the COVID-19 High Performance Computing Consortium, which was set up in the United States, which tried to augment more than 6.4 million CPU cores and more than 49,000 GPUs, totally augmenting to what we call as 600 petaflops. The computing capacity of a supercomputing facility is generally measured in terms of what are called as flops, which correspond to the number of floating point operations per second that the system can efficiently handle. So in this case, it was exceeding around 600 petaflops as such, and there were more than 114 projects which were dedicatedly working on finding out this drug as such. Now, with all of this kind of effort, the consolidated effort that was being put, and this is just a snapshot of the kind of effort that was taken up in the United States itself. But we all know that there were similar efforts globally, including within the country, where all of our scientists and researchers were trying to come up with an effective drug which could neutralize the coronavirus as such. But at the end, we all know what was the result. In fact, we were not able to come up in a timely manner with the kind of solution that required at that point of time, right? Now, what was the limitation? Again, if you look at the basic problem, the problem of protein binding is very well known to the scientists and the researchers, and this is a typical example of an application which requires supercomputing resources as such. So supercomputing facilities worldwide have been extensively used for studying the structure of the proteins and how they interact and how do they bind against each other and how do they fold, protein folding, protein binding. All of these are typical use cases for a supercomputer as such, right? But despite that, the existing facilities that we had were falling short of coming up with a solution when it was required at that scale, which clearly indicates that the scale of the facilities that we currently boast of in terms of supercomputing facilities that most of the countries are in some sort of race to build. Today, we are already talking of having exascale facilities, which only a few select nations currently possess. And India is also rapidly progressing in to have its own exascale facility commissioned as well. But nevertheless, we have seen the inefficacy of these kind of systems to scale beyond a certain extent when it comes to certain class of problems, right? Now, that is where there has always been a constant quest to look at what are the alternate ways, the alternate models of computing that are available for scaling up the computing power that these systems can offer. So we all know the way the modern day computing systems work, including the servers which build up the massive supercomputing facilities, to the kind of laptops and the mobile devices that we make use of every day. Now, all of these systems are called as the binary computing systems, which basically make use of the electronic voltages across the circuits, which are again built upon using the logic gates as such. Now, the logic gates themselves are comprising of transistors as such. So basically, if we talk about having any particular chip today, we are talking about having millions of such transistors that are densely packed on a single chip of a millimeter by millimeter or a centimeter by centimeter wide as such. So fundamentally, we all understand that the computing systems themselves they do operate on the binary logic as such, which basically makes use of zeros and ones, right? Which are again encoded in terms of voltages and currents when it comes to how these units of information are basically encoded onto some physical entities using the electrical circuits as such. Now, having clearly understood this model that we are currently very well familiar with, now just to distinguish this model of the binary computing to what we call as quantum computing throughout our lecture today, we want to refer this model of computing as classical computing. I think by now, most of you might already be familiar with this terminology because you have already undergone 2 or 3 sessions in this quantum computing course, right? So I'll not be going to the details of the introductory concepts as such, but nevertheless, yes, just to distinguish between what we already are familiar with as how we do the computation, we call it as classical computing, just to distinguish between what we are trying to introduce as quantum computing throughout this presentation as such. Of course, we know that the quantum computers make use of something called as qubits, which are distinctly different from how the classical computers work by making use of bits as the basic unit of information. And I'm sure by this time, people have already introduced about the concept of superposition and entanglement and how these qubits are basically built or how these qubits are basically encoded using multiple modalities. It is sufficient now to understand that when we talk about quantum computing, so quantum computing basically it is an alternate model of doing computing compared to making use of the binary logic, which we are all familiar with, and distinct from the way how we employ the electronic circuits for realizing the computational logic. The quantum computers basically make use of the quantum mechanical principles for doing the computation, right? So that's basically what we call as a quantum computer. And of course, the basic unit of information is called a qubit in terms of quantum computer, analogous to what we have as a bit, which serves as the basic unit of the information in terms of a classical computer. How does the entire computing workflow look like when it comes to quantum computing? Of course, as I told, the basic unit of information is called as the qubit. So in any quantum computing unit, you will have a bunch of these qubits available. And this will serve as the basic unit of storing the quantum data as such. And it is on these units of information that the operations will be performed. Very similar or very analogous again to how we store data in our classical terms in forms of bits. And we try to do the operations on these bits of information. So the unit which performs these operations on the qubits, it's called as the quantum processor. Again, if you try to draw an analogy with the classical system, we have something called as a CPU, which will try to operate using certain instructions on the data as such. So very similar to that, we will have something called as a quantum processor, which will try to operate on the qubits for realizing some computational logic. And this logic will be implemented in multiple forms. And the idea behind implementing this logic, we call it as a quantum algorithm as such, which is expected generally to deliver a speed up compared to its classical counterpart. Because that is the whole point of why we are moving on to quantum computers, because we are expecting that these algorithms, that when we try to run it on a quantum system, should deliver a speed up compared to our classical system or our existing systems that we are all familiar with. Now again, what are the kind of problems that these quantum algorithms are trying to solve? Now these are again some of the problems which we are very familiar with, which we are again trying to solve on our traditional systems, be it problems from drug discovery or from the financial sector or from optimization. These are some real world problems that our computational systems are put to use for today. And we try to solve the same problems in a much efficient manner. At least that is the hope. Can we solve these problems in an efficient manner, or at least some of these problems where we have hit the limit, some of these problems where we have the scalability issues when it comes to the computing power as such with the classical systems available? Can we come up with a quantum algorithm? Can we come up with an equivalent which can solve the same problem in a much efficient manner? So that has been the quest for driving the quantum computing research and development today. So when we say that we are referring to a quantum computer, though a quantum computer is a familiar word these days, it can again be ambiguous, and it can actually refer to multiple things when we look at the details of how the computation itself happens. Now there are different ways in which a quantum computer can function, or the different ways in which a quantum computer can be built as such. There are these boxes which you can see on the left top corner, black boxes, which are called as the quantum annealers as such. Now these are some specialized quantum computers which again make use of the superconducting principles for realizing the qubits themselves. But basically, these are some specialized devices which are very much suitable for solving some specific classes of problems, including what we call as the optimization problems as such. So these kind of systems are commercially available today. You can see that this picture demonstrates one such offering from a famous company called D-Wave, which has been into the commercial production of these kind of quantum annealers onto the market. Now, there's another form of quantum computers which are called as the measurement-based quantum computing systems, wherein you try to have large entangled cluster states qubits that you try to create with, and then you try to do the measurement, the quantum measurement on one of these qubits, and then you try to subsequently proceed with the successive stages of computation with that. Now, this model is also quite popular among the industry as well. Particularly some of the companies who have been into manufacturing the photonic based quantum computers. They have been experimenting with this kind of model to come up with a scalable quantum computing solution. And then we, on the bottom left corner, we have this huge chandelier picture, which is by far the most widely seen picture. When you just try to do a Google search for a quantum computer, this is the most widely encountered kind of picture, which depicts what is called as a universal gate-based quantum computer. So basically, it means that these systems are supporting universal computational logic, which means to say that any kind of computational logic that can run on our classical systems, you can still make that logic to function on a quantum computer, right? So that's why these systems are called as universal quantum computers. And of course, they are based on gates, computational gates, quantum gates in this perspective, very similar to how we have our gates that are available in our classical model. So any circuit that has to be implemented can be implemented using these gates in turn. Big giants, big tech giants like IBM, Google, they have all been investing on building quantum computers using this technology, which happens to be more promising when it comes to the support of the kind of applications that these systems can support, because basically they have been shown to be universal theoretically. That means to say that any computation logic can in fact run on these kind of systems. So all of these systems can theoretically they can have applications in multiple application domains as such. Then of course there's another model of doing quantum computing called as the topological qubits, wherein which major players like Microsoft and others have been trying. In fact, Microsoft not very recently, but it has been quite a while, they came up with a commercial chip called as the Majorana, which also had a promising roadmap for scalability as well. And these systems again have some kind of inherent resistance to noise, and that is the reason why Microsoft is heavily investing on this kind of architecture. And then there is another form of quantum computers, which are called as quantum simulators. Now, these are again basically specialized devices. Basically, the purpose of these devices is to mimic the quantum mechanical, to mimic the other quantum mechanical systems as such. For example, if you want to study a chemical reaction at the quantum mechanical level, then you can model the entire reaction using these specialized devices. So these are called as the quantum simulators as such. In fact, these are the basic or the predecessors of all the computation models that we are today talking about when we talk about the quantum computing. In fact, quantum computers were originally thought of, at least that is what Richard Feynman famously said. When he referred to as quantum computing, he was referring to this quantum simulators, wherein specialized devices could be built for modeling the quantum mechanical systems by themselves, for understanding them in a better manner. Okay, now we have talked about different ways of doing quantum computation, and at the heart of every quantum computer, we have this what we call as qubits. Of course, all of this might have already been covered, so I'll not be going into the details of the formalism in which the qubits are represented. When you try to come up with an algorithm, of course, you will have to be aware of how to represent the qubits, how to deal with them, how to construct the gate operations on them by making use of the principles of superposition and entanglement, of course, which are the promising candidates for giving the speed up in terms of algorithms. Since it is already covered, I will not be going into the details of these things. What we want to understand at this stage is that superposition, which is, of course, a fundamental quantum mechanical property, this property can speed up the calculations, right? I'm not sure if some of the quantum algorithms have been introduced to you already, but nevertheless, in the due course of this FDP, I am sure that there will be talks by many eminent speakers who will be teaching you multiple quantum algorithms, and they try to do a comparison with their classical variants just to highlight what is the kind of speed up that these algorithms can offer. Now, superposition, of course, is one of the basic phenomena, basic property as such, which can bring up or which can contribute to the speed up as such, right? Now, with this, you can have the exploration of multiple states in terms of search spaces. You can do a search on a bigger search space as such. All of these things could be accomplished just by making use of this property of superposition in a much efficient manner as such. And of course, what we are basically trying to solve or look at, a major class of these problems are all what we call as exponential problems, which means to say that any known algorithm, classically, these algorithms are all exponential in terms of the complexities that are involved, be it the space complexity or the time complexity. People from the computer science domain, you appreciate what we mean by the time complexity or the space complexity of an algorithm. So we all know that there are these classes of problems which are classified as NP hard as such. These problems, some of these problems have the known algorithms, they're all exponential in nature, which means to say that the complexity increases exponentially with the increase in the data, right? Now, again, this is just an illustration to show the way in which the increase will build upon, or the power of compounding, as it is said. Now, there are a whole lot of problems which are called as, again, grand challenge problems, which exhibit any known classical algorithm exhibits this kind of behavior, wherein solving them efficiently on our modern day classical systems will become a big challenge. And that is the reason we are looking at alternate models for solving the computation. So can we make use of the quantum superposition for coming up with an efficient solution for such problems? Of course, one of the very famous algorithm, which most of you might have already encountered, or which most of you might have already been introduced to in the earlier lectures, is again this integer factorization problem. Now, in the best known classical algorithm today for solving this particular problem, basically, when we say integer factorization, we are looking at given a product of two integers, two prime numbers as such. If we have the product, can we factor the prime numbers as such, right? So this is the integer factorization problem. Now, the classical known algorithms, they are all exponential in nature, which means to say that as the size of the numbers that we are trying to deal with, as the size increases, the complexity of these algorithms increases exponentially, right? Which poses a fundamental limit on what kind of problems can be really solved on our existing classical systems today. Now, why is this problem so significant? Because this problem is at the heart of all our cryptographic systems that we employ today. The public key cryptographic systems that we are all familiar with, the RSA algorithm, at its heart, makes use of this operation as the fundamental unit which provides the mathematical strength or mathematical complexity which delivers the strength for the cryptographic algorithm that we are making use of, which basically means that since we do not have the supercomputers today or any other known computing model which can efficiently break these systems, we assume that these systems are cryptographically safe, right? So that has been the assumption. And it just happened that in the year 1994, this gentleman who is shown in this slide, his name is Peter Shor, he came up with an intelligent algorithm, a quantum variant of an algorithm, which tries to solve the same problem in a polynomial time, right? So any algorithm which still is polynomial is very much desirable rather than having an exponential algorithm as such, right? So there was no known polynomial algorithm for doing this integer factorization problem as such, for solving this problem as such. And Peter Shor's algorithm tries to accomplish the same in polynomial time. Now, what is the implication of this? The implication of this is that today we have an algorithm which can effectively do this integer factorization in a fixed amount of time or in a deterministic amount of time, which means to say that the assumption on which our cryptographic systems were built, saying that it is not possible to do this kind of operation, and that is why our cryptographic algorithms are all safe. Now that assumption no longer holds good, because we have an algorithm which can efficiently break or which can efficiently do this kind of computation in a polynomial amount of time, right? Now, this has again led to lot of implications. In fact, this has led to the whole quantum computing space itself receive a big impetus, because all the governments across the world, they were all jolted when they said that the current day cryptographic system that we are using is all at risk if the quantum computers are made available with sufficient capacity in the future. Now, there's another famous algorithm which is called as the Grover's algorithm. I'm sure again the details of these implementation of the algorithm themselves will be again covered as part of the other sessions. So I'm not going into the implementation level details of these algorithms as such, but just trying to cover the entire landscape of the quantum technologies as such, and the kind of implications or the use cases that these technologies will have. Now, this is again another famous algorithm called the Grover's algorithm, which happens to provide a quadratic speedup for doing a search on unstructured data. Now, doing a search is a very well-known classical problem. And we all know that the worst case complexity is that, I mean, if there are n elements, the worst case complexity is that we will have to search all the n elements for finding out the result of the search, right? And of course, the average would be n by 2 in any case. Whereas this intelligent algorithm that was devised by Grover, he came up with an algorithm which provides a quadratic speedup of the search operation itself. Now, this again had a very big implication. Now, let us again take a cryptographic system, for example. Let's say that we are talking about a symmetric key cryptographic system, which makes use of that ES as such. Now, if it makes use of, let us say, 56-bit keys, then we will have 2 to the power of 56 different key combinations. So if somebody wants to do a cryptanalysis by performing a brute force attack on this algorithm as such, he should go through all of these keys, all of these different 2 to the power of 56 combinations as such. Right now, this is a huge number, and performing a search on this huge number is almost not possible with the kind of computing capabilities that we are having, or at least it is not within the reach of producing the results within a timely manner as such. Now, if you make use of the Grover's algorithm as such, it provides a quadratic speed up, and because of this, the search space itself will get reduced drastically. With this reduced search space, it still becomes possible. It becomes well within the reach of our modern day systems for doing a brute force attack, right? So both of these algorithms, both the Shor's algorithm and the Grover's algorithm, have got significant implications on the cryptography as such and the security systems that we are all making use of in the modern day today. Now this slide tries to capture the breaks of the RSA crypto system in the recent years using the conventional computation. Of course, as you can see that it has reached a limit with the advancement of the classical computers, and anything beyond that is generally classified as the risk that emanates from the quantum computing, which is unknown or which is unexplored at this point of time. But theoretically, we all know that given a sufficiently powerful supercomputer, I mean a quantum computer, these cryptographic systems are largely at risk. Right? Now, what do we mean by sufficiently powerful quantum computer? The modern day quantum computers that we have, the current generation of systems that we have, they severely lack the capacity for running these algorithms to produce any meaningful results to have a big impact as such, right? There are a whole lot of challenges involved in constructing large-scale quantum computing systems, but nevertheless, the technology has been progressing at a very fast pace, and we already have systems which are promising to deliver the qubits in the range of thousands to few thousands of qubits in the coming years. So with such powerful systems available, it is indeed posing a big threat for the modern day cryptographic systems that we are all aware of. So this slide tries to capture the different facets of the cybersecurity systems that we make use of, the cryptographic system that particularly that we make use of, and how they are affected either by the Grover's algorithm or by the Shor's algorithm as such. When we do have the quantum computers which are sufficiently powerful in the future. So as you can see, our symmetric key cryptographic systems, including the AES and the triple DES, and these hashes like MD5, all of these are vulnerable to the Grover's algorithm as such. And the public key cryptographic systems, including the ones of the RSA and the elliptic key cryptographic systems. Now, these are all vulnerable to the attacks from the Shor's implementation as such. Right? So all the known applications of these cryptographic systems in the cybersecurity area as such, be it in terms of building the public key infrastructure itself, or for accomplishing federated authorization, or accomplishing key authorization on key disk key exchange, all of these applications will be at risk in some way if we have these systems available in the future, right? Including the blockchain transactions, which again make use of the ECC or the elliptic curve cryptographic systems as such, which again has a huge implication on the way the cryptocurrencies are being used today. So with this threat known from okay. So with this threat known from the quantum computing systems, or what are called as the quantum attacks on the cryptographic systems, how do we shield ourselves, or how do we come up with systems which can counter these kind of attacks? So there has been a long I'm sorry, there has been some talk. Okay. So there have been attempts on coming up with algorithms, cryptographic algorithms as such, which are considered to be not prone to the attacks from the quantum systems as such. Now, these kind of systems are called as post-quantum cryptographic systems. Basically, these are again classical algorithms which do not make use of the primitives that are known to be vulnerable, that are known to be prone to attacks from the quantum systems as such. There are again multiple ways in which researchers have been trying to come up with these kind of different algorithms. And this is again an ongoing exercise. So people come up with some algorithm to be quantum attack resistant, and there is other set of people who try to attack this and they try to prove that this is indeed vulnerable. So this is again an ongoing exercise. Ultimately, we hope to have a certain class of algorithms which are still sufficiently safe from the kind of quantum attacks that we are expecting. Okay, so having understood in brief about the landscape of quantum computing, now we will just move on to understanding what we mean by quantum communication, or what we mean by quantum networks as such. Now, we are all aware of the standard layered model when we talk about our classical communication infrastructure. In fact, there is this famous OSI 7-layered model, which most of you might be teaching to your students, and which most of you might already be employing when you're trying to build up some solutions for the communication stack as such. Right now, just to simplify the model, again, there is this simplified TCP/IP model, which again has some 4 different layers, which tries to combine the functionalities from different 7 layers of the OSI stack as such, right? Now, if we look at having an analogy between this simplified TCP/IP stack, the 4-layered TCP/IP stack, and how do we try to have an analogy between these layers into the quantum communication stack as such, or the quantum network stack as such, these are the things that we generally encounter. So basically, in the physical layer, we have to deal with mechanisms for creating the qubits. And then we will have to deal with mechanisms that will efficiently generate entanglement. I'm sure we all know what we mean by entanglement by this time, right? And entanglement happens to be a very basic primitive for most of the quantum communication protocols as such. So it is a resource that has to be consumed in most of the quantum communication protocols, including the basic protocol called as the quantum teleportation. Right, and then we'll of course have the channels by themselves, be it in terms of fiber, or be it in terms of free space or satellite, whatever might be the communication channel. We will still have the classical and the quantum channels. And then at the link layer, we will have components which will be responsible for this entanglement generation in an efficient manner, and to distribute it across the communicating parties. Right. This again a very significant requirement when it comes for implementing most of the known quantum communication protocols. As when it comes to the network layer functionality, we have something called as routing, which is considered to be the typical functionality network layer is assigned with, right? So how do we achieve a corresponding functionality in terms of quantum networks? We have something called as long distance entanglement, which is realized using something called as entanglement swapping, right? So that's how you try to achieve entanglement, or you try to distribute the entanglement between two nodes or two entities which do not share a common link between themselves. Then, of course, at the transport layer, we have the end-to-end connectivity in a standard classical model. So here we are talking about the qubit transmission from one entity to another entity as such, right? So this is the basic analogy of having the quantum communication network along with the standard TCP/IP based layered model that we are all familiar with. When we talk of building quantum communication networks today, we generally deal with photonic qubits. By far, photons are widely used for encoding the information and sending out on the quantum channels as such. We all know that the photons are very well employed already for doing the classical communication in terms of optical fibers being extensively employed. This is again one of the advantages that we have if we can come up with efficient technologies that can be used for building and operating these kind of quantum networks. And if they can somehow be interoperated with our existing classical network backbone, then we will have a significant amount of reduction in the kind of investment that we are looking at for replacing the classical communication infrastructure with the quantum communication infrastructure or the quantum network infrastructure as such. And that has been the reason why most of the networks have been trying out to be built using the photons as such. So photonic qubits, as most of you are already aware of, basically make use of photons for encoding the information about the qubits. It could be, again, using multiple degrees of freedom. It could be using the polarization as such. For example, you could call the horizontal polarization as 0. You could call the vertical polarization as 1, or it could be the other way around. The diagonal and the antidiagonal polarizations. Or you could use the different paths in which the photons would travel. If it travels in one particular path, you call it as 0. You designate the other path as 1. So like this, there could be multiple degrees of freedom which could be employed for encoding the information about the qubits by themselves. Now, interestingly, once the qubits have been encoded using the photons as such, if you want to perform some operations on these qubits, basically, in terms of quantum computation, when we say that you want to perform some gate operations, how do you achieve doing these kind of gate operations on the photonic qubit? You again basically employ some optical devices which will try to bring about some changes in the degree of freedom that we are interested with. For example, you make use of mirrors, you make use of beam splitters, polarizing beam splitters, half-wave plates, quarter-wave plates. So all of these kind of optical devices that we still make use of in our classical communication as well. So these systems could be very well made use of for realizing the gate operations on these photonic qubits by themselves, right? And this happens to be one of the advantages of making use of these photonic qubits as well. One of the major requirements for having a quantum network realized is to have an efficient single photon source, which means to say that you have a setup, a source which can emit single photons in a very efficient manner. Now, this has been an active area of research worldwide in coming up with very efficient single photon sources, because once you have these kind of very efficient sources built, they could have applications both in computing as well as in communication as such, right? And when we say in communication, we're talking about multiple components that will require these kinds of things. It could be at the sources by themselves, or it could be in the repeaters. All of these devices that we are foreseeing for building the futuristic quantum network backbone as such, they make use of these single photon sources very extensively. So there are multiple ways in which people have been trying to build up these single photon sources. One of the popular ways is called as the SPDC, or what we call as spontaneous parametric down conversion. So today, people are also trying to miniaturize this entire setup onto a chip, so that these kind of sources are readily available to be used for multiple applications as such. But nevertheless, largely, these kind of systems are all probabilistic in nature, which means to say that the outcome in terms of single photons as such from these systems are all probabilistic in nature, and they're not deterministic. There have been multiple attempts to build even deterministic sources as well. Now, again, this is just a snapshot of the compilation of various kinds of single photon sources. Now, this list is maintained from the institute called as the Raman Research Institute here in Bangalore. And it also tries to summarize or capture the various features of all of these single sources as such. Now, most of you might have encountered this famous terminology called as the quantum key distribution, which again happens to be one of the most popular application of quantum networks today. So today, when we are talking about quantum cryptography or quantum networks, invariably, we will have to deal with this quantum key distribution. So basically, what we mean by quantum key distribution, if we are talking about our classical symmetric key cryptographic systems, again, when we say symmetric, basically we mean to say that both the sender as well as the receiver. So in this case, if we designate them as Alice and Bob, both the sender and the receiver will make use of the same key for doing the encryption and the decryption operations. That's why it's called as a symmetric key cryptographic system, right? Now, since both of them have to make use of the same key, now how to share this key in a secure manner between these two communicating entities, because these two communicating entities will be distributed geographically apart. And how do you share this key, which is very sensitive or which has to be kept secret between only these two participating entities in a secure manner? So this is what's called as the key exchange problem or the key distribution problem. And there have been very intelligent mechanisms which have come out even in the classical scenario, including what we are all completely familiar with, what is called as the Diffie-Hellman key exchange algorithm as such, right? So there are, of course, many other efficient key distribution schemes. Ultimately, they all try to ensure that the symmetric key that is used for doing the encryption and decryption is exchanged in a secure manner between both of these participating entities. Now, of course, with the kind of attacks that these systems are prone to, there are, of course, various kinds of attacks that could be possible, including what is famously called as the man-in-the-middle attack, when they try to steal the symmetric key or the secret key which is being shared between these two entities, right? So in order to overcome these kind of problems or these kind of limitations, the quantum key distribution is proposed to be the solution. So basically what it tries to accomplish is to achieve this kind of key exchange between the two entities in a secure manner by making use of the quantum mechanical principles as such, right? Now, since the key exchange happens, or since the key exchange mechanism itself leverages the quantum mechanical principles, the security is guaranteed by making use of these principles. And this does not rely on the mathematical complexity, unlike our classical algorithms, which we try to make use of in our modern day systems. Because of this, these kind of systems, the quantum key distribution systems themselves, are known to be resistant from the quantum attacks as such, right? Which basically means to say that we are trying to build secure systems which can be used for communication in our next generation communication infrastructure as such. So there are again multiple ways or algorithms for accomplishing the quantum key distribution itself. You might have heard multiple protocols by this time already. Something called as BB84, some protocols which make use of the entanglement as such. Then we have the measurement device independent QKD. Then we have something called as twin field QKD. There are multiple variants, and each of these variants have got their own advantages, their own disadvantages in terms of what extent they can support on a point-to-point link, and what is the kind of maximum key rates that you can expect from these kind of systems, and what is the ease with which they can be implemented physically on the devices, and what is the guarantee that they can offer when some of these devices themselves can get compromised. Some of these intermediate devices that are involved in the key exchange, if they do get compromised. So what is the kind of guarantee that we have on the overall security of the system, right? So there are multiple protocols, multiple algorithms that are available for realizing quantum key distribution itself. And there are few commercial offerings also by companies today. There have been field demonstrations that have been carried out by multiple companies, including giants like Toshiba, who have been advancing this field as such, and then many research groups across worldwide who have been actively pushing the limits for achieving the point-to-point communication efficiency using the QKD systems as such. So basically, we have the QKD, which will facilitate in the key exchange in a secure manner. And once the keys are exchanged in a secure manner, then both the entities can still go ahead with making use of any classical symmetric key cryptographic systems, be it AES or DES or triple DES, whatever it is. So they will again go on with the symmetric key based encryption systems once the keys have been exchanged using the QKD systems in a secure manner. So during the key exchange process itself, of course, if there is an eavesdropper in between, then the QKD protocols have been devised in such a way that the sender and the receiver or the participating agencies can actually find out whether there is indeed an eavesdropper and whether they have been able to access any portion of the data that is being shared in a secret manner. So if at all that kind of eavesdropping happens, then both of these entities can just drop the key that is being currently shared, and they can proceed for the next round or the next iteration of sharing the keys in a secure manner. So this is how the QKD mechanism itself is built, and it tries to solve the problem of having an efficient mechanism for secure key exchange between the participating entities. So having looked at both quantum computing and communication technologies as such, now in some sense we also looked at the kind of use cases that the quantum communication or the quantum networks have to offer. Now let us come back to the kind of use cases that the quantum computing systems are expected to work upon. most of the applications that are envisioned to get benefited from the quantum system, they can be broadly classified into these buckets. The optimization problems, be it from different sectors, the optimization problems are known. Most of the optimization problems as such are known to get benefited from the quantum systems. And then, of course, simulation, which we already mentioned, is again simulating the quantum mechanical systems as such on a completely engineered quantum computer. Now, these again have a wide range of applications in multiple sectors, including quantum chemistry and then the pharma sector, all of these sectors, wherein we are trying to build new materials, come up with new materials with interesting properties, and can we design very efficient electric batteries as such, right? And then the quantum computing model can also be used for enhancing machine learning as such. And I'm sure, again, a lot of discussion in this angle has already taken place during the discussions in the earlier lectures. So the usage of quantum computers can have significant impact in multiple machine learning use cases, including the sampling or the classification. All of these tasks will definitely get benefited by making use of the quantum systems as such. Now, I told you about the quantum annealer, which is again a kind of specialized system. Now, these kind of specialized systems are very well suited for solving what is known as the optimization problems. So there have been advancements in the way in which any classical optimization problem that we want to solve on a quantum computer, the kind of formalism that it expects, there have been multiple formalisms which are supported by these systems. So how do you effectively translate between our classical problem, the optimization problem that we are trying to solve, into a way in which these annealers or in which these quantum computers can understand and try to give an efficient solution? So there are mechanisms today available using which you can translate most of these kind of problems onto the quantum annealers and expect a better solution from these systems. Optimization, of course, finds its space in multiple domains, be it in terms of traffic optimization or optimization for logistics and fleet management, or optimizing the smart grid as such, and urban planning, cybersecurity, climate predictions. All of these areas, we all know that optimization has a big contribution as such. Now, just to speak of a particular case study wherein it was demonstrated that the quantum algorithms indeed have an impact when it comes to the optimization as such. The Volkswagen company did take up a case study in the city of Lisbon, a Portugal city, for doing a pilot study. Basically, they tried to do a bus routing optimization, which employed around 26 buses. And of course, the goal was to minimize the traffic congestion and passenger delays as perceived by different classes of passengers as such. So the algorithm was devised as a hybrid algorithm, which means to say that a portion of it ran on the HPC systems or the classical systems, and the other portion ran on the quantum systems as such. So the results were indeed promising. The optimized bus routes that were obtained as the results, they indeed delivered significant benefits, which resulted in improved passenger travel times. And of course, it demonstrated the utility of making use of the quantum algorithms for solving the real world optimization scenarios as such. So this is again a snapshot from the same Volkswagen pilot study, which was carried out in Lisbon.
Sir, you are not audible.
Hello, wait for the 2 minutes.
Okay, there is, sorry for that interruption. Let me continue. There's another case study which was taken up in the city of London, again, for optimizing the traffic. So we all know that like any other major city, London faces very heavy congestion with millions of daily commuters. So this particular problem was taken up for optimizing the traffic light systems as such. So if they can be adapted, if they can be made adaptive in real time by making use of these algorithms as such. So indeed, once these kind of algorithms were devised and the results were again very promising, we were able to see the significant improvement there with the optimized traffic signal timings, which in fact translated to reduction in the delays and the bottlenecks. And one of the other major achievements over here was that this entire solution again relied on real-time data that was gathered from various IoT sensors across multiple intersections, including the various IoT sensors, the cameras, and the GPS as such. So the algorithm itself had to work on all of these different kinds of data elements as such. So this again basically was a hybrid workflow which involved both HPC as well as the quantum parts as such. Yeah, like I said, the results were very promising, wherein the average congestion time was reduced by 20 to 30%. And it also resulted in improved emergency vehicle routing, because this happens to be one of the hard problems that any vehicle routing has to take care of, right? Which again translated to better energy efficiency because of the reduction in the idle times as such. Similar exercise was also carried out in the city of Tokyo for optimizing the metro train departure and the arrival times. Of course, the goal was to minimize the delays and to handle the unexpected disruptions in a graceful manner, which again has to contribute to the improved passenger experience overall. So this was again carried out as a consortium, as a collaboration with multiple companies, including the well-known names, this again made use of HPC in the backend along with the quantum systems. And this also clearly demonstrated the utility of using the quantum algorithms for solving the optimization problems as such in a very efficient manner. So like this, we can just go on speaking of the different applications for smart cities as such by making use of the optimization use cases itself, right? So we all know the modern day smart cities do employ millions of such IoT devices which do capture data and they do push all of this huge data onto the infrastructure. And we have the real-time data streams on which these algorithms have to function, right? So there will be complex optimization needs that will be required for coming up with solutions for all these use cases as such. Today, we are talking about having hybrid applications put into place, which means to say that there will be classical systems, including the high performance computing systems that we are traditionally familiar with. They make use of, or they are very good at handling these kinds of large data as such and the real-time streaming requirements. And the optimization part alone will be pushed on to the quantum accelerator, and that's how they work in unison or they work in conjunction as such. Okay. And of course, quantum systems are also looked at for future proofing all of these urban infrastructure, be it the communication backbone or the computing requirement for coming up with the next generation, for solving the next generation challenges as such. Then we have another class of computers, which we already saw, what are called as the quantum simulators, which try to mimic the behavior of the quantum mechanical systems in our engineered quantum computing system that we have built upon. So this will again have a very big application in multiple domains as such, including quantum chemistry, material science, like I was mentioning already, can come up with new materials with all the desirable properties that we want for any particular application as such. It will also have big application on the pharma sector as such, and of course on the quantum chemistry itself. We all understand that modeling the chemical reactions on our classical systems as such, there are huge limitations that the systems pose today. If we want to model the entire quantum mechanical behavior of these molecules as such, for a sufficiently large molecule, we do not have enough resources available today which can efficiently model this, because basically we are talking about simulating the many body simulations, which again is very complex to be simulated on our classical system as such. So in order to efficiently simulate and understand these reactions in a much efficient manner, we will need quantum computers or quantum simulators which can efficiently simulate these systems as such. And this can, of course, lead to significant breakthroughs in drug discovery, new material discovery, and of course, improvised batteries, which tries to model the entire chemical simulation, the chemical reaction that happens in a battery as such, for coming up with much increased storage capacities and higher energy efficiencies. We will have to come up with these reactions accurately and efficiently modeled on using the quantum computing systems as such. So quantum computers can definitely contribute to all of this. Then again, we have this universal quantum system, which we talked about earlier as well. Now, this again has a huge range of applications. Like I said, these can run any computational logic that we can think of today on the quantum computing systems as well. But whether the quantum systems can offer speed up for all classes of applications, that is something which is not that promising. Today, we all know that the quantum systems or the quantum computing systems will not replace our classical systems in the near future, but rather the systems will be made use of for solving certain classes of problems, including the optimization, the simulation kind of problems that we just talked about, wherein they excel or they are known to provide speed up compared to their classical counterparts. So though in theory, the quantum systems are capable of running the universal computation logic as such, it may not happen that all the quantum algorithms offer a better speed up when compared to their classical variants as such, right? So that has been the focus of most of the research initiatives worldwide, wherein we are trying to look at how to employ the quantum systems as accelerators, which can work in conjunction with the classical systems as such. Basically, the intensive part, the compute intensive part, which these accelerators are very efficient in handling, they will be separately augmented. They will be separately offloaded onto these kind of accelerators as such for their efficient execution. And of course, machine learning systems have a lot of quantum computing systems have a lot of applications. Like I already mentioned, in different ways, in different aspects of in different aspects of machine learning, the quantum computing systems can definitely contribute to. And owing to the kind of limitations that we have in building and operating these systems today, we are operating in a regime where we have the data available today in classical terms as such, and we are trying to make use of the quantum systems for operating on this classical data. But of course, the expectation is that the systems will eventually transform to a way in which we have the quantum data on which the quantum computing systems will try to operate upon for doing the machine learning tasks as such. Having looked at the various use cases, what are the time frames in which we are looking at the adoption of these use cases? Like I said, there are several use cases which can already be demonstrated in the early stages of quantum computing as such. The current generation systems, which I'll just go to this slide, and probably I'll come back to the other slide later. So the modern day systems that are available today, we call them as noisy intermediate scale quantum systems, basically, which means to say that all the qubits that we are trying to deal with, they are inherently having noise to deal with, right? So anybody who wants to make use of these systems have to come up with intelligent ways in which they will have to deal with this noise, either in terms of quantum error correction mechanisms or quantum error mitigation mechanisms. So all of these systems. Nevertheless, there are certain classes of problems that can immediately get benefited with the kind of systems that we are already having. And in terms of the technology capability or the technology maturity as such, quantum key distribution, like I already mentioned, has in some way got mature. And today we have commercially available systems demonstrating QKD over significant distances. And then we also have quantum annealers, which are available in the market, and then atomic clocks, which can operate with a very high precision. They're also available today for commercial usage. In the near future, we are expecting that these technologies will evolve for having quantum safe networks, and then quantum imaging, and then also producing some kind of preliminary advantage by making use of this NISQ era computing systems. And of course, the broader expectation is that in the future, we will have these systems significantly contributing to quantum machine learning and quantum simulation, which can have again implications in multiple significant domains, and also leading to something what we envision as quantum internet, which can have profound applications on its own. Okay, yeah, so we just understood the quantum use cases and then the kind of adoption timelines that we were looking at. Of course, there are various classes of business and industrial applications that could very well get benefited, including the supply chain optimization or the cargo loading optimization, the portfolio optimization in terms of the finance applications as such. And then, of course, when it comes to the molecular simulation, including the protein folding, which we discussed in the beginning of the presentation itself. So all of this could get significantly impacted. And then the integer factoring or the prime factorization, which has got a huge implication on the cryptography and the cybersecurity that we make use of. And quantum computing systems can also have significant applications in sustainability related sectors, including on green agriculture, on trying to model how to come up with efficient fertilizers and how to study the nitrogen fixation, which happens in a very efficient manner naturally. How do we try to model them and how do we try to mimic them using any of our artificially built fertilizing systems as such? And then clean electricity, clean manufacturing, and then of course green mobility by having more efficient electric vehicles, and then hydrogen powered transport. All of these things can very well be impacted by making use of the quantum computing systems. So having understood this whole gamut of quantum computing and communication and the kind of use cases and the application that they can have impact on, I'll just try to conclude my talk by introducing some of the initiatives that CDAC has been involved with in terms of quantum technologies. CDAC has been actively working in building indigenous technologies for both computing as well as communication. So we were proudly associated with the Indian Institute of Science for coming up with an indigenous superconducting based quantum computer, which is currently deployed and functioning at IISc Bengaluru. And CDAC was instrumental in building the control and instrumentation hardware for the system. And we also have a product called as the quantum simulator, the QSIM simulator, which boasts of having more than 7,000 users. This is basically a software package which can just be accessed online for running all your quantum circuits simulation in a very efficient manner and in a very easy manner. CDAC is also involved in working on what are called as quantum accelerators, employing multiple classical accelerators for enhancing the quantum circuit simulation as such, and also looking at how quantum computers can work as accelerators to the traditional HPC systems, and what's the kind of hybrid application workflows that could get benefited from this architecture. We're also involved in setting up a physical quantum computing system itself. We're expecting that we will have a 50 to 100 qubit quantum computing system established at CDAC in a short span of time from now on, which could be used researchers across the country for various applications and algorithm design as such. In terms of quantum communication, very similar to our computing simulator, we also have a product called as the quantum network simulator, which can simulate multiple communication protocols, the quantum communication protocols. And we are also working on something called as a metro area quantum access network, as part of which we have demonstrated a successful quantum key distribution network, a testbed which has been laid out physically, connecting 3 different research institutions, 3 different agencies in the city of Chennai. And we have been able to successfully demonstrate the QKD over existing fiber network between these two, between these 3 intersection nodes as such. We're also working on drone-based QKD, of achieving QKD with moving targets. CDAC is also proudly involved in setting up the national quantum communication backbone of the country, which spans for over 2,000 kilometers, starting from the city of Chennai, including Bangalore, and then finally it moves on the way to the city of Delhi. So once realized, this will be the national quantum communication backbone of the country, which is being implemented along with many other institutions in which CDAC is also a proud member of for implementation. Like I said, work on the post-quantum cryptographic solutions on systems which will help us in securing ourselves from the kind of quantum attacks that we are foreseeing. These are called as the PQC systems, and CDAC has been actively working on these systems. We are coming up with our own complete PKI stack, the public key infrastructure stack, which is resistant to these kind of quantum attacks. So we will have the PQC implementations of algorithms on this stack as such. And we will also have these algorithms to be implemented in a very efficient manner on different accelerators, including the FPGAs. And then we also have PQC compliant USB tokens, which could be used for various operations like signing and many other things, which we generally make use of by making use of the cryptographic dongles. And we are also working on a huge number of use cases by making use of quantum machine learning, which has implications on different use cases and applications from multiple sectors as such. So with this, I formally end my presentation. I hope through my presentation, I was able to give a glimpse of what we mean by multiple quantum technologies when we say quantum information technologies as such, in terms of quantum computing and quantum communication, and the kind of broad implications that these technologies are expected to have in the near future.
Yes, sir. Participants, if you have any questions, you can ask. We have one question from the participant, sir. Miss Preeti Bitra wants to know, do we have a scope in the agriculture?
Yes, there is a huge scope in the field of agriculture. Like I was mentioning, one of the ways in which people are trying to employ the quantum simulators as such is in the development of new fertilizers as such. The other mechanism which people are actively trying to study is in the field of nitrogen fixation. You might be knowing that there are these class of plants called as the leguminous plants, which have this special properties of doing the nitrogen fixation. The nitrogen that is atmospherically available, they do fix them onto the soil, making the soil very fertile for growing various other crops as such. Right now, how do we come up with efficient fertilizers or efficient mechanisms through which this same process, which happens in a very efficient manner in a natural way, how do we make this kind of systems available? How do we make these kind of processes to be happening in a very efficient manner by making use of any of these kind of fertilizers that we try to build, right? So in order to do that, we will have to understand the nitrogen fixation process itself in great detail, right? How exactly this process happens in nature. To study this process, of course, we will require quantum computers to be available, because the kind of molecules that are involved in these reactions, the current day systems, the supercomputers that we are having today, they do not faithfully scale up for modeling these kind of reactions in a very efficient manner. And that is one of the reasons why we need quantum systems for studying these kind of reactions in a very efficient manner. So in short, yes, agriculture has got multiple applications. Of course, the very basic phenomena of photosynthesis itself is shown to make use of the quantum mechanical phenomena as such for achieving very high energy efficiency.
Okay. Thank you so much, sir. One more question we have. Mr. Gaurav Tavde has asked, is it possible to use quantum computing in wireless networks?
Wireless networks, yes. So we talked about quantum communication networks, and the communication channel could very well be fiber, or it could also be free space. So the quantum communication protocols have been implemented and they have been demonstrated both on fiber-based terrestrial networks as well as on free space networks, including wireless networks as such, and satellite-based networks as well, right? So definitely they do have applications in wireless as well.
Okay, sir. Thank you. Any more questions, participants?
Sir, as you said, this will not replace the original one. But since the data is continuously increasing in every field, so people will prefer quantum computing compared to normal one and algorithms of quantum computing compared to the normal one.
It could be, ma'am. It could be, though we do not have sufficiently capable quantum computers today. Like I said, the technology is progressing in a very rapid manner, and we will be having very powerful systems, or at least that is the hope, that we will be having very powerful quantum systems in the future. And once we have these systems available, definitely it can process much larger amounts of data. It can also run much complex algorithms, which will definitely have some kind of quantum advantage demonstrated compared to what we are classically seeing with our existing systems as such. That is at least the hope.
Yes, sir.
Yes.
Sir. Okay, sir.
Sir, as you said that we do not have capable quantum computers yet in the today. From what I understand, the biggest problem lies in the technology involved. That is the superconducting qubits. They do not operate at the room temperature. So we need some new materials that operate very well at the high temperatures, or at least at room temperatures. So, sir, since you talked about topological materials and Majorana platforms in one of your slides, so can you tell that what materials are trending or more bright future in research?
Yeah. Like you said, materials definitely are one aspect which will drive the way the technology progresses in the future. Definitely new materials which can be the efficient candidates for any of these platforms that we are talking about. They will definitely contribute in a very significant manner. Today we are also exploring, can we still make use of the traditional semiconductors that we are familiar with, be it silicon or be it germanium? Can we make use of these semiconductor platforms by themselves for building the quantum computing systems as such? And in fact, there have been very promising results. And in fact, giants like Intel have also demonstrated that this is indeed possible, right? So there is, I mean, this is again an ongoing exercise, and there is no clear guess that anyone could make on what is the kind of possible discovery that can happen in material science. But nevertheless, there are multiple contenders today. And like I said, there is no one winning candidate that you can pinpoint today telling that this will be the future of all the quantum computing systems for tomorrow. And it is because of this, all the technologies are seeing advancement as such. So there are certain classes of computing models which some companies are trying to advance. Then the other set of companies are building on the other set of materials, the other set of computing models and things like that. So today it is all in the state of evolution, and we don't have a clear winner available today. And of course, it is not that all the models that we are talking today do require the superconductors to be made use of, right? That is just one model of computing which makes use of the superconducting materials, which again requires a huge setup for bringing down the temperatures to millikelvin. The materials start behaving like superconductors. That's again one class of materials. There are other ways in which the quantum computing systems could be built, including the ones which you just mentioned, the topological qubits, or they could be the photonic implementations by themselves, which basically do not make use of ultra low temperatures as such. But nevertheless, for doing some kind of detection or some auxiliary operation, you might require the systems as of today. But the model itself, the fundamental model itself, might not require very low temperature operations as such. So like I said, there is no clear winner when it comes to what will be the go for platform for tomorrow. But people have been experimenting all of these things, and we don't know which will really click in the future.
And sir, we experienced that there is a lot of advancement going on in the quantum computers, and it is faster than expected. So, what do you predict that how long it will take to quantum computer to mature and take place of traditional computer?
No, like I said, even though there is, even though there will be advancement in the field of quantum computers themselves in terms of scale, we do not see that they will be replacing the existing day systems in any way, because though they are capable of running all sorts of computational logic, we expect them to cater to certain classes of problems which they will be very efficient in doing. Okay, for example, optimization itself, right? So it is these classes of problems for which the quantum computers will be used as accelerators, which means to say that you will have the classical systems anyway required, and the quantum computers will act as accelerators, which will work along with these classical systems for the future generation systems also. And this has been the model in which the modern day systems are also, in which they have also got evolved. For example, you take the example of GPU itself, right? So GPUs are specialized accelerators which were built for doing the graphical operations in a very efficient manner. Today, of course, they are being used for doing some other general purpose computations also, but traditionally they were devised for doing the graphical related operations, graphics related operations in an efficient manner. So very similar to that, today we have math accelerators, we have crypto accelerators. All of these different accelerators are available today. They work in conjunction with what we call as the CPU or the main computational unit. Very similar to that, the quantum systems are also capable of handling certain classes of problems in a very efficient manner. And it is this kind of conjunction in which they will work, which is what is expected to be in the near future.
Okay, sir. Thank you, sir.
Okay. Okay. Thank
sir,
you.
Sir, we have a couple of questions.
I'm really sorry. I'll have to rush for another meeting. So I'm sorry, but anyway, I'll be available for contact later on as well. So I request the organizers to kindly share my email ID with all the participants who might have some possible questions. Please excuse me, since I have to rush for another meeting, I'll have to take leave at this stage.
Okay, okay, no problem, sir. Thank you so much.
Okay.
So, as the session is over, I conclude the session. It was really a informative and content-rich session, sir. You explain all the details of quantum computing, starting from the fundamentals, then the processor architecture, then you switch on to the quantum algorithms, their significance, and the cyber security. Then you explain us about all the use cases and applications of the quantum computing. So it was really a wonderful session, sir. And thank you so much on behalf of the organizing team of this ATAL FDP. I thank you so much.
Thank you, ma'am. And
Thanks a lot.
my sincere thanks for all the participants who had been patient in listening through my lecture. And my sincere thanks to all the organizers also for giving me this opportunity to interact with you all and share my ideas with you all. Thank you.
Yes.
Thank you.
Thank you, sir.
Thank
Thank
you,
you
sir.
for
Thank
giving
you.
your
Thank you.
valuable time. Thank you, sir.
Thank you.
Hello, participants. Small announcement is there. Our second session speaker is having some medical emergency, so he will be not be able to join the session. But Dr. Pallavi Sapkale, she is ready to join the session. So she will join us in at 7:45. So you all be there in the meeting. At 7:45, we will start our second session.
Hello, Dr. Pallavi.
Not joined yet, Ashish.
Yes, she has joined.
Hello,
Hello.
Dr. Pallavi. Hello, am I audible, Dr. Pallavi?
Pallavi ma'am, if you are joined from Teams app, then please log off and join through web browser. I think there is some issue with the Team app today. Hello, Dr. Pallavi. Yeah, you are still not audible.
Hello, sir. Ashish, sir. I'm
Yes,
audible?
Shaista ma'am.
Yes, sir. I have a talk. She's joining from other device. She's having some technical issue in one device. So she's joining in while with other device.
Okay, okay.
Hello.
Yes, ma'am, you are audible now.
Hello.
Okay, okay. Thank you so much. Yes.
Yeah.
Hello, Dr. Pallavi.
Yes, ma'am. I'm
Yeah,
audible,
this is
right?
yeah. I'm audible.
Yes, ma'am. Yes.
Yeah, this is Dr. Amruta Ruperi. Thanks a lot, Pallavi madam. In a short notice, you accept our request and agreed to deliver the session. Thanks a lot, madam. Now I request Shaista madam. She will introduce you to the participants and then we start the session. Yes, over to Shaista madam.
Yeah, thank you so much, ma'am. And again, thank you, Pallavi ma'am, for accepting at the short notice. So, Ms. Shaista Khanum, Assistant Professor and Co-Coordinator for the ATAL FDP. On behalf of Organizing Committee, I warmly welcome you all to the Day 3 of ATAL Faculty Development Program. It gives me immense pleasure to introduce our eminent speaker for the next session, Dr. Pallavi Sakpal. She has earned her PhD from DJ Sangvi College of Engineering, University of Mumbai, and brings with her over 16 years of rich academic experience. She is currently serving as a professor at Ramrao Adik Institute of Technology, Nerul, Navi Mumbai. She is an active member of IEEE Bombay section and presently serves as a secretary of Women in Engineering, WIE, IEEE Bombay section. In addition, she is a life member of EAI and Soft Computing Research Society and IST. Dr. Pallavi has an impressive research profile with more than 25 publications in reputed international journals and conferences. She holds four granted international patents and has 10 Indian patents to her credit. She has also authored 4 books, and her forthcoming book on quantum computing to be published by Willy is eagerly waiting. She actively contributes to the research community as a reviewer for IEEE, Microsoft, and Springer, has served as a technical program committee member and session chair at several international conferences. She was also honored with the Best Paper Award at Technovation 2020 Jaipur. Her research interests span quantum computing, machine learning, wireless communication, VNet, 5G and 6G networks, wireless sensor networks, and AI ML driven communication systems. We are truly honored to have her with us today. I now warmly invite Dr. Pallavi Sakpal to take over the session and share a valuable insights with us. Thank you, ma'am. Over to you, ma'am.
Hello,
Yes, ma'am.
I'm audible, ma'am?
Yes, ma'am. Yes, you are audible.
Yeah. Thank you, madam. Thank you for the kind and generous introduction. I'm truly grateful for your management that Vidyavardhini College of Engineering and Technology and respected principal and the head of the department for giving me this opportunity to interact with you as a resource person for this FDP on this quantum intelligence, exploring the convergence of quantum computing and AI. I'm so thankful to organizing team also for their dedicated efforts in making this program for this success also. And first, I will also thank to the all participants and congratulate to that participants for joining this faculty development program and their enthusiasm for the exploring emerging technologies and also continuous learning and such a collaborative platform which are essential for the teachers also, so which will help shaping the future and the education research also. So congratulations for all the participants and thank you for the management. Now we will start the session as ma'am told. Ma'am, please adjust the session and I started this session also. So if there will be something will happen, so please bear me. Okay. Yeah. Ma'am, can I start the presentation?
Yes, madam.
Okay, okay. Okay, it will take some time. Yeah, it's my pleasure to hear with among all the passionate academicians, and I hope today's session will be informative and engaging. Yeah, is it visible, ma'am?
Yes, ma'am.
Yes, madam, it is visible.
Okay. Thank you so much, ma'am. Now we'll start the session. Let's begin with the some of introduction about me as ma'am already given. So the quantum communication networks. So my topic I will started with the trends and the challenges. Here in this quantum communication networks, now day by day there are lots of changes. So before going to introduce all the points, we'll just go through this table of contents. We can see here uh, the introduction to the quantum, and what about the quantum communication, then what about the networks, the challenges, and somewhat the demo about the hands-on I will just adding in my this talk. So before starting this session, I just introduce about the what is going on this era about the security. So today almost everything from the banking to defense, which is depend on the more and more the security communication. So here also the security is the most important thing which will required for day to day life. So but what if I tell you that the future computer can be break today's strongest encryption? Is it possible in the future? Maybe yes. This is not science fiction, but it is consequences that quantum computing will give such a platforms. So we can just make that it will the security will be the most powerful thing in the future. So the nature question, my natural question is that how do we protect this communication through the quantum world? And will we happen or will be happen such things with the security? So I think yes. So the answer for this line is a quantum communication network, and that only the part we are introducing here for the quantum computing and quantum communication, which is very important throughout this security about the future network. Just we can say that for the military purpose, for the defense, for the banking sector, so there are the very personal things where very important things are there, and for such a purpose the security is the most important point. And through this quantum we will all the things can be feasible with this quantum communication and quantum network. So here the content only can see that these are the points which are very important related to this quantum communication and quantum computing networks. So we will first understand about the basics about the communication, and then step by step we can go about the architecture and the platforms and the networks and the future trends. Okay, so hope you see interest in this quantum computing and quantum communication networks. So before going to all the depth, I just want to ask you, what about the quantum? Now this is the third maybe or fourth day. So everyone is started about the basic things about the quantum and all, right? So you know the basic communication or basic purpose or basic definition about the quantum communication. So here I just want, so do you know about the quantum basic, everyone? Okay, maybe yes. So we'll just start. The quantum means a smallest possible unit about the energy or the matter. So the quantum is very tiny, and according to this quantum, here the light exists as a packet we can call as a photon. So energy levels, which is a very fixed for this uh, smallest particles or smallest possible unit, and we can say these are not a continuous. So here we'll also focus that particle which can behave as a both waves as well as in particle forms. So these are just basic about the quantum. And this small particle, how the particle will be useful for the communication and how we can compute the particle about this quantum. So that we will be see here in the future networks about the communication. So this is not a basic physics which is 0 or 1 or something similar or conventional behavior about the quantum. So we can see here the changes how the quantum can use for the communication and how the traditional is changes to the advanced one, that we will be see here in the quantum communication network. So before going to enter the depth, we can see here the experiment with respect to the coin flip. Maybe everyone given this example also. So what we can use, we just flip the coin. So there will be some observation. If we are flipping the coin, maybe during the toss also. So what happened? In the first step, we can observe here at the end, we can see either it will be head or it will be tail. At the second point, we can say here, it will be the probability that H means head or it will be tail. Maybe both are equal, means 50-50. So the probability says that it can show the tail or it can show the head. Means we don't know that point ki what is the exactly head or what is the exactly tail. So that time we can say the 50-50, and means half of the percent is head or maybe half of the percent is tail. But the third point can say that during the flipping stage, we cannot decide it will be head or tail. So same consideration we can use for the quantum communication or quantum computing network. Like that, we cannot use this state in the conventional part. We can only consider it will be head or it will be tail, means it will be a 0 or it will be 1. But with the help of this quantum communication, we can possible with both the states, which we can see here. Now this analogy with the bits, see here as I told you, if we can say the tails or we can say the heads of the coins when we flip in the air, so that time we can see the head part is the bit 1 and the tail part if we consider bit 0. So what happened when we flip the coin and the coin will be fall down, that time it will be head or it will be tail. So means head if there, then the coin said that bit said that 1, it will be tails, the coin said that 0. But the coin is just like as the while spinning, the coin is in between that. So we can say the probability half up. So not a head, not a tail. So that time when we such a condition can see that there is a joint probability having 0 or 1. So we can consider the probability with that 1 is equal to P or 0 plus P or 1. Means probability of 0 or probability of 1. Both can we say that half of the part is the possibilities. So that means the probability we can consider here. Now, with this example, we can correlate the things with respect to the atoms. So how we can correlate? See here, I will explain you. When the atoms in the spin up state, it is 1. And when spin up down, the state will be 0. As we see first slide, it is head and tail. If head is there, then we can consider 1, or it tails, we can consider as a 0. So the correlation about the atom, we can see here when atom is the moving part, and it will shows that head means 1 and it's down, it will show as 0. So but when they are transitioning from which state, that we don't know. So probability we can define according to correlation about this atom. See the example about the qubits. So here I show some diagram about the interactions for the qubits. So in this slide, the wavy surface, there are two surfaces. One is the uh, platform is simple and another one is some kind of the wavy surface. So this represent as the quantum energy, which landscape or potential field. So in this, the dots, see these dots, so that each small dot which represents here the quantum particle such as an electrons, or we can say as an qubit. So the ups and down which we can see here according to the platform. So these are the ups and downs for the surface which show how energy varies due to interaction between the particles. Now here the blue means here the cloud like region we can see here, that region which represent the quantum wave functions showing where particles are most likely to be found. And when these wave functions overlap with each other, so we can say that the particle begins to interact or becoming a correlated. So, and here we can see the interaction arrow. So that arrow which label with the some green part, we can see here, that is the interactions. So that how the particle influence with each other will be easily find out with respect to this interaction. And in this middle line, the dotted line, we can say that this is shows the possible path for the coupling between the particles, which we can see here. Now, some particles see here, some are in the diagonal form, some are in the vertical form, some are in the horizontal form. So means the probability we can find with respect to the direction or with respect to the movement about this qubits. So here the red cross which are showing in the next part, that will be marked for the unfavorable, or we can say as a forbidden state, where interaction or movement is not allowed due to the energy constraint. So this is the example we can consider in the qubit. Uh, Here the simplest qubit and bit, how we can define or how we can compare with each other, that slide is described. So here in the bit, as a conventional one or traditional one, we can say as 0 or 1. So that is the single bit we are using with a simple and the reliable form. And this bit can say sometime 0 or sometime 1. But in the qubit, what happened? In the qubit, we can say simultaneously 0 as well as 1. Both can use at the same time. So this can the most important thing and interested thing is happen with the qubit. How? So here the quantum basically use on the qubit platform only. So this qubit is totally depends plus 0 and plus 1. So we can use both the things, both the bits at the same time with the superposition. Maybe you already seen in the previous quantum lectures that superposition and the entanglement is a very important thing for the quantum. So same thing, what is the meaning of this superposition is when we are using simultaneously both the bit. See, in the previous things, means in traditional work, bit are only we can use a single platform, means only 0 or only ones at the same time. We cannot use both the bits at the same time. But qubit, in the qubit we can use both the bit at the same time, means that is a very major important thing we can see here in the qubit. And that thing is happen with respect to this superposition. The next part we can say as the entanglement. Entanglements, only the qubits connect in the powerful ways. See, whenever we are considering these qubits 0 and 1, so the entanglements, though the bits are very present at very long distance, then also they are interconnect with each other, because they are having very powerful energy, and due to the entanglement part, the qubit connect with each other, but they need extreme stability to work. So that is the main drawback we can say for this qubit, is they are mostly not stable. So according to that, there will be some noise or interference will be occur. So we see here what is the difference between main conventional bit versus the qubit. Now see, this is the basic principle for the quantum computing. In this principle, we can say, as I already told you, the superposition, entanglement, and the interference. These are three basic points are important for the quantum computing. And because of this quantum computing, we can just easy for our communication part, and we can see the for long distance also, and for uh, short distance also, we can use all the type of this communication part. So here the first we consider that the superposition. As I told you, superposition, in the superposition 0 and 1 simultaneously work, but in the classical computing that bit is only for the 0 and 1. So this allows the quantum computer to process many possibilities and simultaneously, which work together. So next part we see here the entanglement. Now entanglement means what? There are two or more qubits which become a connect each other, and when the state of the one qubit which change, the other changes instantly happen, even if they are far apart. Means just like you can say, as one person is standing over here and another person in very far from, or very using long distance with each other. And then also, if the entanglement part is there, if the quantum entanglement we can consider, so they can communicate with each other through this process. And the second one we can say as the interference. Interference, which is used to strengthen the correct answer, or we can say the cancel out the wrong things. Means what? I want to give one example over here. Like suppose the person, we can say as Alice and Bob, the example we are considering in the next slide also. So if Alice wants to communicate with the Bob, and if the key is divided with the Bob and Alice both, and then during the communication, if they occur something is happen wrong, so at the time the communication will stop, because they are not getting any accurate bits. So that time the interference, due to this interference, it will stop, and the security will be more for that communication. So such type of the interference we are using in this quantum computing. Now basic bit, this diagram may be aware to everyone. Hope you all know this, that is called as the qubit. So here qubit is showing the bit is 0 and the bit is 1. So here upper part we can say that a 0 part and the 1 part. So with respect to this 2 bit, we are formed that qubit. So qubit is nothing but the superposition which help do away from this binary constraint and working of the quantum computer, which is based using about the particles in the superposition, and rather than it representing that bits, such a particle which represent this qubit, which can take on the value of 0 and 1, or we can say as both simultaneously. That is the major advantage about this superposition, and it will only use in this qubit. So the criteria we can see here for the superposition, which refers the quantum phenomena where quantum system can exist and multiple states or places for the same time. So we say that it can use for here and there, or we can say as up and down, as we seen the qubit before with respect to the platform communication. Then here a quantum also can hold the information which is using with system, And we can see that there are the two systems which we are using 0 and 1 with simultaneously. So this qubit can simultaneously store with a 0 and 1. So here two types qubits can simultaneously hold for the four values like 0, 0, 0, 1, 1, 0 and 1, 1. So these are the important thing, and it will be clear when we can take a hands-on session for the Q universe. So it will be easy to understand with respect to that hands-on. So here we see that the classic example for the superposition qubit is that, as I told you, when head and tail example we can use. So half of the part we are considering for the quantum communication. So same time, the possibilities that we are using 1 plus 0 at the same time. So here we see the classic computing. Here we see the bits stored either 1 or 0. And then see, this is the quantum computing and the superpositions with respect to the qubits, which can store anywhere from 1 and 0. So see the example when we are considering this eta or the entanglement and the superposition for this qubit. So that time we are considering the half of the eta 0 and the half of the theta 0 and half of the theta 1. Means the probability for both is half. It will be 1, it will be plus 0 and it will be plus 1. So both we can use the simultaneously. So there will be some basic laws which we are using for this superposition of the qubits. Here the evolutions about the quantum theory and the quantum technology. See, the quantum is the evolved from the early quantum from 1900 to the till date. We can say that from 20th century. And today, the advancement about this quantum processor developed by companies like IBM, like Google, and there will be the growth about this company and the quantum, which they are using in the advancement. So here we can see that all the advancement is occur with respect to the company with the different years, and now the IBM is using major technology and major quantum technology for this quantum communications. So basic computers, like we can see the 216 qubit. We can see here the 216 qubit. Then we can see here the 32 qubit, which is developed by the IBM. 127 also qubit developed by this IBM. And here we see that Zhang quantum computer, which shown here that 76 qubit. So these are some quantum computer which look like this. Here we see that how the different from the quantum computer and the classical computer. So when we are computing, there will be some question like how the quantum computer will work with the both states. So I want to say that here the computing is takes place with respect to the n qubits, okay, in the quantum computer. But in the previous, it will use n bits. So how the classical bit and how the quantum bit will be differ with each other, we can see here in the classical computer, the bit we are using only one state, means n bit state. But in quantum, we can say that the bit is 2 raised to n components. So here we are using, suppose n is equal to 3 here. So we are considering only 0, 0, 0, 0, 0, 1 up to 1, 1, 1. But when we are considering in the quantum computer, we can say that alpha theta is 0, 0, 0 plus beta 0, 0, 1, and all the possibilities condition we can consider here in the quantum computer. So see the diagram also. Here basically only the symbol we are using in the traditional one and in the quantum one. So hope you understand this example. There is the very simple example I am using for this difference for quantum computer and the classical computer. Now, our main important thing, that is the heart of this topic, we can say, that is a quantum communication. So is the quantum communication possible? Anyone? Is it possible nowadays? Yes, it is possible. We can see with the growth of the quantum technology sector in the recent year, this quantum computing will be, or quantum computing is giving some advanced communication method through this quantum. So we can use the quantum. There will be one example also that I also want to discuss with you. So what, before that, we can say what is the quantum communication and how this communication will take place. So, according to the quantum communication, if the quantum are available easily, and we can see the communication with respect to this bits. So, how the bit will be travel and how the communication and can be happen with respect to the transmission about the bits, that we will be see here. So, the quantum communication is used the bits for the transmission, and about this transmission to encoded about with a quantum information from one place to the other place, and then only the communication will take place with respect to this encoded quantum information. Now the information which is the sender side, it is a encoded form, and toward the receiver side, that form is the decoded part. Means whatever the information we are sending having a most security part, and due to the security part, it will be the very trustworthy part for the defense, for the military, and for the banking sector. So that's why the quantum communication is preferred during these days. Now, quantum information, we say that it is used with respect to the quantum bits like qubits, which we seen in the before previous slides. So, which can exist in the multiple state simultaneously with respect to that superposition and the entanglement, which seen that concept about the superposition and the entanglement, and considering that part only, the quantum information can be sent from sender to receiver. And here the qubit can be both 0 and 1, which is simultaneously used in the superposition form, and they are according to the same data from one place to another place with the crypted form. Now, how this thing can happen? So major focus on this slide only. How this quantum communication is take place. Yes, ma'am. Any? Hello. Is it audible, ma'am?
Yes, ma'am, you're audible.
Yes, ma'am.
Okay. Okay. Any questions? I think some voice raise here.
No, ma'am,
Is
we'll
it
take
okay?
the questions at the end, ma'am.
Okay.
Or,
Okay.
huh?
Okay. Okay, ma'am. No problem.
And if
Yeah.
anyone wants to, like, we don't want to discontinue or
Okay. Okay.
continuation.
Yeah. Yeah. I think I. Okay. So here we see the how does quantum communication will work. So as I already told, superposition, that qubit exists with the multiple states like 0 or 1 simultaneously. So due to that superposition, here in the quantum communication, the faster and secure data will be sent. Means if we can see that here the probability of both the bits, means 0 and 1, simultaneously sent with the superposition. So that's why the data or the you can say as the message, that will be faster and the message will be secure. So how it will be secure? Because the sender is using the crypted data, and in the receiver side, the data will be decrypted with respect to the QKD. So what kind of this QKD? QKD is nothing but this quantum key distribution. So these are the three steps which we can use in the quantum communication works, or we can use in the mechanism about the sending and receiving the data, which is very important for the quantum communication. So you see here in the main, entanglement and superposition are the very important thing. So entanglement we can use to link the particles that instantly reflect about the changes like secure data transfer, or during that time it will be helpful to use that QKD, and QKD means quantum key distribution, which is preventing for the prevent from the dropping of the call or dropping of the bits. So when entanglement is happen, so that time the sender which are sending the data with some secured key, and this secured key is known to that person who is received the data with the transferring about the secure transformation, or secure whatever the information, whatever the data, what the thing he sender want to send, the data will be received toward the receiver with the highest security. Then next part we can say as the interference also. So during the dropping of the bits, the sender can whatever the data sender send, and during the time of the sending period, if the data is misplaced and it not get to the receiver, so that time receiver also know about it, data will be somewhere leak or somewhere it hack. So that time automatically, due to this interference or entanglement process, the data will be changed or the system will be stopped over there, and this is the very secure position will happen in the quantum communication. So see the diagram here, quantum communication distribution, any interception disturb for the quantum state, and it is basically use the example about BB84 protocol. Sorry, now I will explain you how this protocol will work with respect to the mechanism about this working protocol. This protocol is totally depend upon this quantum key distribution. Now see, I want to explain this with respect to some mechanism, and here only the quantum communication will happen with respect to the this QKD, and we can also consider this example about the BB84 protocol. That will be very important example. So I will explain this with respect to this simple mechanism about the quantum. Now see here some message which is sending through the Alice. Okay, and this message is a encoded message. Suppose Alice want to send some message to this Bob. So what happened? If the message only know this Alice, and this Alice wants this message to the receiver side, means toward Bob's side. So that time what happened? Some key is encoding here. So this key is known to sender Alice, and this Alice wants send the bit like 0 or 1. Okay, that time he only using the single photons into two bases. Now how he are going to use the single photon? Now here the Alice encode bit only 0 and the bit is 1. Both are bit he is using with single photon, and the bases he is using, that bases are 2 bases. Okay, so during that time, which basis? The first base is, we can say that that is the rectilinear basis, and the second one we can say that that is the diagonal basis. So here in the rectilinear base or basis, we can say at it is used in the rectilinear form, and in the diagonal it is used like a diagonal form. So when these two bases Alice can consider, and the bit is 0 and the bit is 1. Here also we can say diagonally this bit is 0 and the bit is 1. So both these bases we can consider this photon and sent from this Alice to Bob. Okay, and during that time the photons are sent one by one. So single photon will can send, and that time this measurement toward this receiver side, what happened here? Bob randomly chooses one of the two bases, means here we can consider this two bases. And what happened here? Bob knows the message. Bob is only collecting the message from this R, means rectilinear and diagonal form, which two bases form, and Bob will choose randomly two bases for the measuring about the photon. But here the basis about the public channel, whatever the key, means cryptographic key will be present, which is sended from this sender to the Bob, means Alice to Bob, that publicly compare the bases, and not, if it found that not bit or any bit is missing or bit is not found, means that time the sender Bob can matching the bits with the sending Alice bits, and if the bit is misplaced or the bit is not matched, so that time the any kind of the message will be dropped and the message will be stopped over there, and mismatch bases are discarded here. So if the matches about the bits are not equal, so the message will be, or sending message will be stop over there, and the bits is a discarded. And the matching base, if the base or two bases, any kind of the bases will be matched, so bits will be kept ahead and the message will be given to the receiver side. So such kind of the working principle will, or working mechanism will happen during the sender and the receiver side with respect to this consideration about the PB84 protocol. And this is the most important or highest security which use in the quantum communication. So that can be happen with this quantum key distribution channel or quantum key distribution we are considering here is a basic part about the QKD. So during this mechanism about the quantum communication, only the part is just we are sending the message from Alice to Bob. Okay, but if during this form the bases are not matched, then the message will be discarded or the message will be stopped. And if the bits are matched, then the message will be sending toward the continuation form. That only the part we are understand with respect to the quantum communication part. Now, next we are considering this photon preparation. Then we are considering here the quantum state selection. Then we are considering photon transmission here, and detection, then keys shifting and the error. And according to that only the working mechanism and the working principle will take place about this quantum communication. This is the very important part. Now we see why this communication will take place over here. So during this quantum communication, we are considering, or we can say that this classical encryption, which is becoming vulnerable, Then it will be give the secure long distance communication. Then again use for the unbreakable security. As I told you before that, as the bits are not matched, the security as per the security purpose, the message will not send to the sender side and it will stop. So such kind of the highest security can use in the quantum communication. So that security is a unbreakable part, and we are using this security here for the quantum communication. Now, next one is the high trust communication. That is the ideal for the defense, banking, and the for government sector and for the military purpose also. Next is the enable quantum networks, which found for the quantum internet, then critical for the finance, military, and the healthcare also. So that's why we are using for the major high security, the quantum communication will take place. Now I will say that what about the quantum communication will work in India. So maybe you all aware about it that India also achieved the significant milestone in the quantum communication with the successful demonstration with the free space quantum secure communication over the 1 kilometer by DRDO and the IIT Delhi. You can say as this is the best part for the India that this communication will take place successfully for 1 kilometer. And recently some China also using the same communication. I will talk about that in a later slide. So here see that the quantum communication which happen in the global market for this is the report from 2025. So we can see that the growth from 1.18 billion towards now we can see here the 27.7% growth is occurred till 2029. So basically what kind of the quantum communication, as I given one example for the Alice and Bob, so that only the concept we are using for the quantum communication part, and such method is transmitting this information using the principle about the quantum mechanism like quantum entanglement and the no cloning theorem. So here we can see that quantum entanglement, how this phenomenon will work for this diagram. So here the basic thing is the host A, B and C are using, and with respect to this host ABC, there are this part are the end user part, and this end user we can see like quantum nodes also, and they are sending the information means in the form of the qubits, and the information will send and receive through this node A, B and C, which is the host ABC. So they want to send the information in the secure form, means most important security will be used here, and the message or data will be transferred. So here the next part we can say as a switching also there we can say as a Q switching, which that switching are used in the quantum information or quantum switch, which works like as a router. So this router which helpful to send in the quantum networks, and they create entanglement particle for like qubits, and this particle which help to pass the entanglement from one node to other node. And next one we can say here Q repeater. Q repeater is nothing but our simple repeater that extend the communication distance, means if the communication is less here, so they just extend here from one to another, and it prevent the signal loss also, and help for the long distance. So this Q repeater connect with the multiple short entangled links from one long link. And the next part we are considering here, the main important is a controller. Controller also work like as the basic controller for the classical communication channel. And the responsibility about this controller is used to maintain the entanglement map, then swap the instructions and not handle the qubits. So according to this, the controller will helpful for this communication part, and this quantum entangle will happen over here with respect to the communication about the channels and the host. Now see, this is the example I want to show you that happened here. I just tell you about this free space quantum secure communication over the 1 kilometer by DRDO and IIT. So this is the sign, or you can say as a picture from that communication which takes place. See this green arrow we can see, or green line we can see here. This is the quantum communication happened successfully in India for 1 kilometer distance. The source I took from the internet. Now here the quantum communication how happens in this entanglement part that will be elaborate over here with respect to this securely share the encryption key between these two parties, as I told you, Bob and Alice example. So same thing will be happen here. And how it will be work? It will be use a pair of entanglement photons which is generated here, and then the photon is sent to A and other side, that is the receiver side, to B. And this kind of the things will happen with respect to the quantum key distribution, or QKD. And these are the major applications for the quantum communication used in the India, like highly secure communication for armed forces, then end-to-end secure mobile and internet communication, then a secure command and the control system, and the protection from the future quantum based cyber attacks. So cyber attacks is the major thing happen nowadays, and this is the more secure and important thing for this quantum communication, because the highest security is used here in the quantum communication. Now India's quantum mission, what kind of the mission India is having? We can see here that 6,000 crore investment is there for this quantum communication, and which is approved in the 2023. So in the coming future or coming days, this thing will be happen more interesting, or we can say as the more helpful for us with respect to this quantum communication. And the second one we can say as indigenous development, then talent development, and that will be the future about India for quantum communication. So this is the main mission India is following. Now we see the challenges about the quantum communication, like single loss over distance, then decoherence noise, then security issues, the expensive hardware, then we can say as a limited quantum repeaters, and error correction difficulties. So these challenges we are faced for the quantum communication. So we can see step by step here. First, single loss over distance. Here, single loss over distance means whenever we are going to use the quantum communication, so that time the long distance quantum signals weak and they are travel through a fiber or air. So if they are traveling through the air, so that time some due to some noise or due to some interference, the channels will affected and the signal will be lost here. The chances of the signal will be lost. So because of that, the high distance or higher distance or longer distance, which is the very challenging part for this quantum communication. And due to the weaken of the signals, it will also affect the communication part. Then in this same distance, if the distance will long, so photon may be absorbed or scattered somewhere, because the photons are affected with this air and the environment. So that time they are just absorbing and the scattering part is the more. So that time the during this communication also not proper. And the limits about this long distance quantum communication, and India and all the countries also facing this challenge, and they are just working some points for this signal and loss over distance in quantum communication. Now, second is the decoherence and noise. Now, quantum states are very sensitive for the environment, or we can say as a heat, vibration, or some electromagnetic noise. They can be disturbed to this quantum communication, and there will be the noise and decoherence will be occurred. So causes about the loss of the quantum information will take place. So remember these things during this communication. There will be the need of the less vibration, and the temperature will be good for that communication. Then only the communication will be healthy, or it will be happen smoothly. Now, next part we can say as the security. Though we are using the quantum communication for the security purpose, then also the security issue will be take place in the quantum communication. How? So the quantum communication will be having some practical devices, and that can be vulnerabilities, and the attacks may occur due to hardware imperfections. So the hardware should be very neat, we can say as the accurate for this quantum communication. Otherwise, the attack will be happen for this quantum communication. So this is the more important thing we see in the quantum communication. And next part we can say here the expensive hardware. So hardware really expensive because they are using some single photon sources, then cryogenic systems, then high precision detectors. So according to this, the cost will be definitely high for this quantum communication, and the hardware also expensive. Next part we see in the challenges like a limited quantum repeaters. So here the quantum repeaters are needed to extend the distance, because we are using from if distance is increases, there will be lots of repeaters are required. So again the cost affecting things are happen here, and this will be affect the quantum repeaters. Then error correction difficulties, because of the quantum data that cannot be copied, and the traditional error that correction does not work. So this quantum error correction needs many extra qubits, and this is the thing continue with the drawback about the communication of the quantum. So these are the major challenges facing by the quantum communication, and many countries are working on this main challenges which overcome here for the quantum communication, and India also main leading for this quantum communication, and he is also trying to give some solution for this uh, upcoming challenges. Now see how many challenges India facing with respect to the communication. We can see here first important thing, as you know very well, nowadays day by day the dust particles are more, and the environment is very dusty during these days. So same thing is happen in the quantum communication also. So it will disturb the communication for the quantum, and there will be the artificial lights effect, and they are free space for the photon transmissions. So we can see here because of the dust particle also, it will be the communication will be affected. And scaling up about the creating multi-node national quantum communication grid, which also used here the in the next like infrastructure gaps which need for the quantum detectors and the stabilization systems, then interfacings that bridging a classical and quantum system securely. So, and most important thing, as I told you, that hardware are expensive parts. So same, India also facing the problem about the costing and the complexity about the hardware, and there will be some high research and development that operational cost is there. Now, I just told you about in the previous slide, I will discuss about the different countries' quantum communication. So see here the chart for the global developments in the quantum communication. So how the communication is happen in the global market. So the China, you can see this news also in the Mrs. Quantum satellite, which enabling secure satellite ground with respect to the QKD in 2016. So same USA also are using this internet blueprint by DOE labs and QKD pilots in the commercial networks. Then there will be some other countries and also working for this quantum communication. And just in 2024, the India also successfully completed about this quantum communications. So these are some example how the quantum communication will work in the market. This is the basic quantum communication versus optical communication. So you can see the difference here. So factor which are matter like photon use in the quantum communication with respect to some uses in the quantum properties like individual photons in while as in the optical communication it uses a large numbers of the photons. Similarly, we can compare with respect to the spectrum here. In quantum communication, the spectrums which operates in visible or near visible spectrum, but in the optical, we already seen like they are both visible and near visible. And data rate also, there will be very secure. And here in the optical one, traditional one is the higher data rates. So same thing we can see here the power output, data transmission, same like as a data link. And these are the basic points we are considering for the quantum communication. Through the communication channel, the post transmission check about the ensures securely, while as the coherent optical link also used in the optical communication. So this is the main difference we can see here in the quantum communication as well as in optical communication. So here next slide we can focus for the trends and future. So as you know very well, now trends are going for the quantum communication are like satellite QKD, then quantum internet, then integrated photonic chips, quantum repeaters, post-quantum cryptography, commercial QKD devices. So these are the trends are going, and in future also these are the important parts. So considering this first part in the satellite QKD, we can see here how this satellite QKD or quantum satellite quantum key distribution here, what is the QKD satellite or why it matters or what kind of the example. So recently we seen the example like a China missile satellite which demonstrated for the secure satellite QKD over thousands of the kilometer, which enabling the global scale for this quantum encryption. So that is the best example for this satellite QKD. And why it matters? Because optical fiber have distance which limited due to signal loss, satellite which can transmit the quantum key globally by sending photons through the atmosphere or the space. And next point we are considering like for the quantum internet. So why the quantum internet is or what we can use it. So the proposed future for the internet where quantum information which is help with respect to the qubits is transmitted between the distance of the quantum communication and the quantum devices. And that is work with respect to this quantum entanglement and the ultra secure data transfer. And they are also used for the new applications like quantum sensing. So this kind of the thing will be important in future. Now integrated photonic chips. So the importance for this integrated photonic chips we are considering like photonic chips which enable scalable, compact and the efficient quantum devices which we are using in the form of sources, detectors, processor, and we are using for the quantum light on a single chips. So this kind of the integrated photonic chips are also in the trends for future and trends. Then we are focusing for the quantum repeater, as I told you, as the number of repeater increases for the long distance. So that is also the future trend for this quantum repeater. Like they can use for the single degrade over the long distances, and due to loss and noise there will be required of more repeaters. And they are also giving some challenge like a building quantum repeater, which is a difficult because they require quantum memory, and this is the more important part, which is a difficult part for the quantum repeaters, because that require quantum memory and entanglement swapping. So for that swapping, the major challenges are there in the quantum communication. Post quantum cryptography, we can see here why this cryptography is needed now. The quantum computers could break the many existing encryption algorithm like RSA, ECC, and for this algorithms to fulfill the criteria, this post quantum cryptography is required. Now we are using some use cases ensure that security, classical data after quantum computer with respect to this, which is very powerful, and also develop some new algorithms like mathematical problems, and also using some example like lattice based cryptography. So these are some part which considering for this post quantum cryptography. And next one we consider, that is the commercial QKD device. In this commercial QKD device, they are also ready to use devices, and it systems that perform quantum key distribution for the secure communication. And the current status about we can see for this commercial QKD, like while still expensive and specialized, and also used for the real world environments for ultra secure communication, and such kind of the things will happen in the future. So these are the major trends and future for the quantum communication. Now someone wants to research for this quantum communication. So there will be the points, or there will be some topics which are interested for this quantum communication, because these are the new opportunities for the researchers, like they are used with the error corrections, photonic sources, quantum memories, and definitely about the networking protocol. As we compare our basic network to quantum network, there are lots of challenges. So these are also a very important point for the researchers. And next is the secure IoT using QKD. So there will be the basic things we seen for the security purpose. Now we are considering that security for the quantum communication using IoT as well as in the QKD. So these are the main important topics. So if someone are interesting to do this in the research, they can definitely use, or you can use this point for the future. Now I want to show you some demo about this quantum computing with respect to the Q universe. So maybe many of you know about this software, or know about this Quniverse. So this Quniverse, I want to say that this Quniverse is developed by the IBM CDAC, and it's a very simple platform which we are using some simple algorithms which use for this quantum communication or quantum computing. So that will be helpful for the researcher, or they are some using some work on the basic quantum communication. So they can use, because this software is free software, and easily understand for the basic concept. And you can use the many small things with respect to this quantum computing in this Q universe. So it will help for the qubit visualization, superposition demo, simple circuits, then entanglement demo, QKD related circuit. You can give the example to your students also in any practical or whenever you are explaining some computing part for the quantum. So you can use this. So if you are interested, I will show you some hands-on session for this. Ma'am, Emma, hello, ma'am.
Yes, ma'am. Yes, ma'am.
Yeah. Can I give some hands-on or the time says
Ma'am, I'll just
any
check.
restriction?
Give me 1 minute, huh, ma'am.
Okay,
Just 1
okay.
Madam, you can give demo, no problem.
Okay, because there I am seeing the time is over, I guess. So
One or two example you can give as in
yeah,
demo.
yeah, I will just show the how the Q universe is open and how we can use it. I'll just give in next 5 minutes.
Yes, yes, madam.
Yeah, yeah. Okay, before concluding, let's see how quantum concept can be explored even without a physical quantum computer with the Q universe. We can see it. Yeah. Yes, participants, you please open your Google platform. If you are able to do, you can do with me simultaneously. See, you can type quniverse.in. Anyone you are doing? You can go with a Google and type the quniverse.in. Just open this website, Cube Universe. See the spelling QNIVERSE.in. And there will be the, yes, quniverse.in. If you open, just register here. There will be some register form, simple one, basic thing you have to enter, and you can enter and register for that. I already registered, so I'm directly logging this. Once you register, you can just start your session with the login. Once I log in here, see the, yes, is it visible, ma'am?
Yes, yes, madam, it is
Yes, ma'am,
visible.
it is visible.
Okay. If anyone doing, please start, or if any problem, you can let me know. Okay. Okay. So here, basically, when we are starting with this, so we are using this Q universe for the quantum communication or quantum computing. So for this quantum computing, there will be some algorithms you require. So basically in this algorithm, I just given same example, simple example about the Hadamard gate. So before going to this hands-on session, I will explain you what kind of the Hadamard gate will be used. So see here the Hadamard gate for the quantum logic gate. So basically there will be superposition theorem, we are superposition thing we are using for the Hadamard gate, and the symbol for the Hadamard gate is H. So how it works? So we can see that if a qubit is in a state, we can say as theta 0, which is applying for the H transform, and the equation will form for the 0 and for 1. So here we can see that Hadamard, which is denoted as H, theta 0 equal to theta 0 plus theta 1, and as the superposition, we can say as both the part as possibilities for 0, 1 divided by root 2. So same thing for the one state also. And the effect we can say in the Hadamard is when the definite state we can say as kita 0 or kita 1, which are into equal superposition for 0 and 1. And that time we can say that the kita 0 output is equal to chance of 0 or 1, or input we are using for the 0 and 1, and the output will get in this form about the different phases. So we see here with respect to the Q universe, just simple I am using as a gate is Hadamard gate. See, these are the different gates we will see here. The red point I am covering, which is the Hadamard gate. And if I am using this Hadamard gate for this Q0, now this Q0 are the input we are using here. Q0, which is the state, see the state as the kita 0. Here Q1, see the state as the kita 0. Here Q2, our state kita 0. So how many states we want? So according to the state we are considering. So here in the first state I am using the Hadamard gate. Now in the second one I am using this X gate because we are adding with the qubit. So here 0 or 1. So it will showing me the gate will be added here. So this is the adding gate. And if you are using this gate in the extension with respect to or with Q0 means Q1 and Q0, if you require for the both of the state, so just go in the edit form. You can select the bit here, add control. So I am adding here next qubit. So here Q0 and Q1 are 2 bits. So first one is the controller bit now, and second one is your target bit. So just save it. So you will get the line in between Q0 and Q1. Maybe it is visible to everyone. Now, whenever we are adding this bit, so there will be required about the measurement gate. So this gate we are using as a measurement gate. So here I am applying the measurement gate. There will be number of measurement gate you can use. And once the gate is applied, so select the thing here after running the program. So you can run this and select any processor whichever you want. Here the processor number are CPU, GPU, FPGA, QPU. So whenever you require any particular processor, you can choose it. Otherwise, you can go as a simple one, CPU one. Now, next one we can using in this configure backend that select HPC. So here also QACC cluster, there are number of cluster we are using like Param Utkarsh, or we can see as the QACC cluster. So with respect to the same, simple we are using QACC cluster. And the second thing is important, which is focus for this select a simulator, and we are using in the backend. So we can go with the simulator. There are number of simulator are listed over here. We can choose any one from this as per our requirement. So here I want to go for the CDAC photonic because I want to show you some photonic simulator. So I am choosing this CDAC photonic simulator. So I submit it. See, this is the green part. We show that your simulation ID returned shortly and my job ID is created. So you can see here 16340 is my job ID, and that job ID is created because successfully completed the entanglement with this circuit. Now you say that this 16340 is just using. Once you get the ID code, then you can refresh it and you will see the graph bar here in the form of the histogram. Now see, this is the histogram which found here, means your circuit is completed and the status for the circuit is also completed, and we are see that a running status also completed. So we can see the histogram for the level 000, 001 and 000. Because I am taking the 3 bits here, that's why it's showing in the 3-bit form. So you see here the probability about the first is 50%, and the probability for the second state is also 50%. Means you can check that if your probability is 40 or 50, means your circuit is not proper, or you can say that if 20, 30, then also your circuit is not proper. Your circuit is probability is equal, then only your circuit is proper. You can check that histogram here. And the next output can visible as I consider here the photonics. So check this photonic circuit. I consider as a photonic. That's why I check this photonic. See the output. You will be see here what is the head mud. And when we giving the kita 0 as an input, you will just beam splitter here and you will get your logic, you will get your photonic circuit. So what circuit I am applying? You can easily see here the circuit in the output also. And as per the given state we are applying here, we'll get the photonic circuit. So and we are applying here QASM. So all the things are in the coded format will be visible. So this is a very, very interesting and very simple part for the quantum computing, and we can give the practical session also for the students. Now see, these are the main parts. Here the quantum composer, which we already composed some example here with the headmud, and there are some resources also. So compute this resource like QASM simulator, AR simulator. So these are the different simulator which can use just like as I'm using the some simulator with respect to this. So there will be detail about the configuration, spin 2 plus, status is there, infrastructure is there. So you can read all these things. If you want any kind of the simulator, you can use the simulator from this compute resources. Like I use this QASM simulator. So there are also some details about all these basic gates, backend names, backend version, which version is working here. So everything is given. Now you can also choose some algorithm, whichever you want. Here basic algorithm details are given. So you can choose anyone like Shor's algorithm, then Hadmard algorithm. So we can, I'll just show you how the algorithm factorization. So there will be some number you can see. See, these are the Shor algorithm, and all the details about the algorithm also given here, and how it will work. They are also giving the details and procedure in this algorithms also. So I request all the participants, you can try once how many jobs you are completed. So jobs also just displayed over here. So you can check it, your jobs, how many jobs you completed or you done. Then some documentation also there. So it will also helpful for you. So this is the basic Q universe. I just give the introductory version to you. Yes, hope you understand or you can interested to this. Thank you so much. Thank you, ma'am.
Thank you so much, ma'am. Participants, you can ask your questions. I'm audible?
Yeah, ma'am.
Yes, Shaista madam, you are audible.
Yes. Ma'am, I have one question. Ma'am,
Yes.
basically, when you compared the Q bit, like 3 bit, you explained 0, 0 to 1, 1. And when we are going with the quantum computing, so you said 0, 0 to 1, 1, all these combinations will be one state. So, ma'am, how like for all the combination is quantum computing is calculating the output at the same time?
Yes, ma'am. Actually, what happened na, as I given one example where during the sending and receiver time. So when we are using the 0, 0 and 0, 1, so there will be the bases. So that basis we are using two bases, and the encoding part which we are using in the single photon. So that time, that's why the communication we are going to use as a 0, 0, and means whatever the things we are considering as per the bits it will be varied.
Okay, ma'am. Okay, ma'am. Thank you so much, ma'am.
Yeah.
Others, you can please unmute yourself and you can ask the question.
Good evening, ma'am. Am I audible?
Yeah,
Yes,
yeah,
sir,
sir.
you are audible.
Shardul, sir. You are
Yeah,
audible.
yes, sir, you are audible. Yes.
In optical communication, generally we require some kind of fiber for transmission. Do we
Yes,
need
yes.
fibers in quantum communication as
Yes,
well?
yes, sir. Yes, yes, sir. Fiber also required in the quantum. Yes.
Okay, ma'am. And what is the if the speed is not there, then what is the advantage of quantum communication apart from security?
So security is the main advantage for the quantum, for the military purpose or for because it's a very secure platform as in quantum communication. So that's why it is a very, very beneficial.
Okay, ma'am.
If there are no further queries, Shaista ma'am, you can conclude the session.
Yes, sir.
Sir,
Sir,
I am
sir,
audible. Am I audible?
yes. Sir, Trupti ma'am is there. So she is going to conclude the session. Yes, Trupti ma'am, you can start.
Okay.
You are audible, ma'am.
Okay, okay. Thank you, ma'am. Good evening, ma'am. I'm Trupti Shah and I will briefly conclude today's session. Ma'am has very nicely explained the fundamental principle of quantum computing, highlighting how qubits differ from classical bits. Session provided insights into the real-world realization of quantum computers and introduces a core concept of quantum communication. The ma'am's talk was explained how quantum communication ensures secure data transmission using quantum principle. She also highlighted India's progress in quantum communication, including key contribution by DRDO and IIT Delhi. Ma'am had also demonstrated Universe hands-on session. Overall, the session effectively connected theory, implementation, security, and national advancement in quantum communication. Thank you so much, ma'am, for your valuable time and insight. Thank you once again for accepting our request at such a short time. We look forward to interacting with you again in future. Thank you.
Yeah,
Thank
yeah.
you so much.
Thank you so much, Trupti ma'am. Thanks a lot. Thank you, everyone. Thank you, Shaista ma'am.
Thank you,
Thank you
ma'am.
so
Pallavi
much.
madam,
Yeah.
thanks a
Before we
lot
conclude,
once again.
I request all the participants to kindly turn on the camera so that we can have a group photograph.
Yeah, yeah.
Pallavi madam,
Yes, yes, madam.
thanks a lot once again, madam.
Thank you so much, madam. Thanks. Thanks. It will happen sometime in our college also. So we just take care
No,
about
in
it.
such
Yeah.
a short notice, you agreed and some delivered very nice session.
Thank you,
Thanks
ma'am.
a lot.
Thank you, ma'am. Thanks a lot. Yeah. Shall I close, ma'am?
1 minute, madam.
Ma'am, your session was like, it was not like looking like a short notice session. It was perfectly, there was nothing like we can say it is short notice.
Ma'am, actually, I want to add something more, but in the short notice, you are just telling me, ma'am, do. So I just wind up everything and did.
Ma'am, we'll have an interaction in future also.
Sure, definitely. I
Yeah.
want to focus on the Q Universe, which is the best
Yes.
platform for the quantum communication, but I just missed it.
Ma'am, we'll have.
I
we'll-
think the
we'll-
participants are also not there, right? 7 only we, yeah.
No, there are participants, but I think so. There are
Actually, we
bit
were
less.
not prepared for the hands-on session.
Yeah.
Okay.
Yeah.
It's okay,
So,
it's okay.
yeah, thank you, everyone. Yeah.
Okay, thank you everyone. Tomorrow again at 6 we will meet. Thanks a lot.
Thank you.
Yes, ma'am.
Bye.
Thank you so much. Yeah.
Thank you, ma'am.